All right, welcome to part three of the Connecting Soil Health and Bigger Deer series that I'm doing here. We're going to start jumping into soil samples, but before we actually jump into some actual examples of soil samples, I wanted to take some time to kind of pick apart some of the things that we'll be talking about later so that when we get to the actual soil samples themselves, we have an understanding um, down to what these things actually are. So, in understanding soil, the first thing that we need to think about is there's chemical and there's biological practices that happen in the soil. A lot of us are really familiar with the chemical processes, but maybe not so much with the biological processes that are going on in the soil. So we're going to touch on some basics of some things and discuss how that can affect our understanding of what the soil samples are actually telling us. So this is a chart that pretty much everyone has seen. Um, Here you have your pH scale. A couple things that I wanted to point out on this is if you remember our discussion about successional growth, the pioneer plants and the weeds always came first in the successional growth, and we know that that soil was really highly alkaline. Well, if we put everything together and look at the chart of alkaline soil and acidic soil, it makes sense that in soil that is highly alkaline, those plants are set up biologically to perform better at that combination of nutrients. As you move through the chart, when you get into that row crops, vegetables, that kind of area we want to be for our perennial food plots, it's a balance between the alkaline and the acidic soil structure. And as you can see by the chart, that makes a lot of sense because that's when the highest amount of the minerals are and nutrients are available to the plant. So don't just look at this as, okay, I know that if I'm at a 6.5, I can have pretty good uptake, everything. Let's start thinking in terms of what plant species thrive in this system. And if I have very strong alkaline soil and I want to plant a perennial crop in there and weeds show up, I have to understand that that's because that is exactly what is going to survive in those conditions. So good chart, everyone should have a basic understanding of where you fall. And when you get your soil sample, what does that mean? In the future, we could actually go into a little deeper as far as what certain plants actually thrive on, which ones plants do better in a certain situation and which do worse. But for now, we're just going to kind of understand that the pH is going to dictate in some manner what is going to grow and what's going to be successful. And if our soils aren't in that area for that plant to thrive, then we're going to have to start thinking about what can we do in the long term to change that and what tools are available for us in the short term to be able to work around that pH issue. All right, in the long term, one thing that we're pretty much all familiar with is the liming. Getting some lime on the soil, trying to move that pH into the more alkaline. Um, what I don't think people have the grasp on is understanding how that pH affects the nutrient uptake. So if we read through this, if you're at a 6, 20% of that applied fertilizer still may be unavailable for that plant to uptake. 7 is everything. If you have 7, those fertilizers are going to be available to that plant once they're soluble, once they're ready for plant uptake. But as we move away from that, we're losing more and more of the fertilizer that we're applying, as it will just never be available to that plant. So if you're down in the 5.0 area, almost 50%, or actually more than 50%, will likely be unavailable to that plant. So we need to take that into account when we're talking about the financial aspect of fertilizing. If we are going to apply the fertilizer to the soil and we're at a pH of 5, we have to have that understanding that over 50% of what we're putting down is just going to be lost. It's not going to be able to be uptaken by the plant. General rules of thumb: 400 pounds of pellet lime equals 1 ton of egg lime, and 400 pounds of pellet lime per year usually gets you to maintain the pH that you're currently at. 800 pounds of pellet lime will raise the pH, and you shouldn't apply more than 1,200 pounds of pellet lime per year. On the egg lime section, never apply more than 3 tons. If you need 6 to 9 tons, if you get your soil sample back, they're telling you, hey, you need 6 tons, distribute that over several years in order to get the desired results that you want to do. Gypsum, that's something that John talks about a lot. 23% calcium, 19% sulfur. Typical application rates 400, 1,200 pounds. Advantages of gypsum is it does have some ability to drill into the soil, create a little bit more infiltration along with the pH factors of the gypsum. So just a side note, this chart right here is in the food plot guidebook. I highly recommend that everybody owns a copy of the food plot guidebook. When it comes to just general information, that food plot guidebook is just packed full of very informational charts like the one we're seeing here in front of us. So another thing that we're going to focus on is cation exchange capacity. And we've had some discussions on this in the past. I think that sometimes we go too deep, too far on it and don't just pull back. What we need to understand is that everything has a positive or a negative charge. Nutrients are positively charged. Organic matter, negatively charged. Structure of soil makes a big difference. So what I try and tell people is, think of that when you rubbed that balloon on your head as a kid and stuck it to the wall. There was a bond there. There was an attraction that held that balloon in place on that wall. Similarly, the soil holds different ions that are positive and negative, and those do have a bond and they hold together. So when you see CEC on your soil sample, what they're trying to tell you is the ability of your soil to have the greatest amount of that bond in the soil that helps to hold things together and not just let the rainwater wash it through your soil, or for it to actually work its way up and expire into the atmosphere. So cation exchange capacity is the total amount of cations that your soil can retain. Now, this is a major issue in sand ground. There's less surface area on the sand than there is as clay. The more surface area we have, the more clay we have, the more negatively charged areas that we have that can hold these positively charged nutrients in the root zone for the plant to be able to go out and get it when it needs it. CEC increases with the amount of clay and also the amount of organic matter. So organic matter can help those in sand ground areas to increase the cation exchange capacity, but just like if you were transferring the soil into a more clay-based system. So you can imagine what it would cost to bring in tons and tons of topsoil or clay into a sand ground situation. It just would not be cost effective. However, adding organic matter to the soil has many benefits, and one of those is to be able to raise the cation exchange capacity. Now, why does this matter? A couple different ways. It can increase the soil pH when in the areas that are needed, but the biggest reason is nutrient holding. Just like we just talked about with the pH having an effect on how many nutrients are going to be able to be uptook by the plant, CEC is going to tell you how much that soil is going to be able to hold those nutrients in the root zone. So basic rule of thumb and kind of a cheat sheet on this is to take your CEC on your soil sample and multiply that by 10. So if my CEC is a 6, I multiply that by 10, that's 60. So 60% of the nutrients that I'm putting onto that soil are going to be able to be held in that root zone by my cations, by the ability for that soil to hold those nutrients in that zone where it needs to be. So if we stop and think about this now, if we have very poor soils and we put down a bunch of fertilizer, we've already knocked a large portion of that off if our pH is not in a desirable zone. And then if our CEC is not in a desirable zone, we're knocking another big chunk of that out. So there are situations out there where we are applying fertilizer to soil and getting very little return on our investment because our pH and our CEC are neither one in an area that allows us to use those nutrients that we are adding to the soil. Okay, organic matter is the other thing that we'll talk about. Organic matter is anything that contains carbon compounds that were formed by living organisms. So dead forms of organic matter, mostly old roots, fallen leaves, old, mostly dead plant parts. That's 85% of the organic matter in the soil. 10% of it's living plants, mostly roots. In the soil, the organic matter, you're going to have your dead plant material and you're going to have your living plant material. Then there's going to be living microbes and soil animals. It's just something that we're really going to focus on as we keep moving through this. And then partly decayed organic matter. This is the important stuff. This is the humus that we talked about that gives that soil that darker tint that is creating the food for the microbiology in the soil. So living roots, covered soil, active biology. That is the fastest way for us to increase organic matter in the soil. All right, so with the conventional way of thinking, we're susceptible to failure. Drought, flooding, pests, weed competition. We need to understand that focusing on biology and not the chemistry is our best defense for successful plots. So in the chemistry that we've just talked about, I laid out the challenges of an off pH. It's going to take a bunch of fertilizer away from us. The challenges of low CEC, It's going to take usable fertilizer away from us. And then low organic matter is also going to have a negative effect on the soil. So what we're going to do in the next seminar is we're actually going to look at some soil sample examples and drill down a little deeper into them to give everybody a better understanding of what you're looking at, and also what kind of examples are out there or options are out there that we can use to get a better understanding of what's going on in our soil. All right, thank you for joining us for part 3. Part 4, the soil sample examples and chemical versus biological, will be up next.